Here is progress on the smart dump load that I've made for the pedal power generator. If you want to know why I came to the conclusion of building it this way, then you can watch a previous video that I made about the pedal power generator. I said I was going to film the build of this, but as with everything, if you film it, it takes twice as long. So this is it in its almost finished state. There's not much else really that could be improved on this in its current way. It works really well for the projects that I've planned for it. So let's have a look at some of the electronics on here. We have the current sensor there, which is measuring the total current that's going into the resistors. We have a reed switch, which is next to one of the sprockets that picks up the RPM. And also that more useful is to convert that into a open circuit voltage, and from those two, current and open circuit voltage, we can get the total power that the generator is producing. So that's internal resistance as well as external resistance. We also have obviously the MOSFETs. They're controlled from the Arduino Every, and we've got their pull down resistors here, and they are actually quite important, as I learnt the hard way. We have a Bluetooth module here, which is transmitting the data from the Every, so that can be logged on a phone, for example. So that explains the basic functional part of this, which is controlled from the Every. And now I should explain what this one's for, and this is going to be used for ANT Plus communication, and it's an NRF52832, and the reason for that is that one project is to measure the efficiency of a NuVinci or NVLO hub. So we're going to take power data from some Garmin pedals, and secondly we want to maybe turn this into a smart trainer. So I want to be able to use the FE-C or Fitness Equipment Control profile to take ANT Plus information from some fancy software like Zwift, for example, and then that can control the resistance. I'm using a separate board for a couple of reasons. Firstly, I'm still not very familiar with writing code on these chips, and secondly because this one is like 3 times the price, and when controlling the MOSFETs that have got like 60 volts flowing through them, I'd rather use a cheaper board for the high power stuff. Got the old mountain bike set up with the Garmin pedals, and today I'm going to have a go at testing the efficiency of this ancient N360, which is the very first one that I bought. And I've got the input locked to the output. I've created this hub internals bypasser sprocket thingy, so it engages with this spline here that's underneath this cover normally, and then this is just a cut down sprocket, and that replaces the spacer that's usually in front of the sprocket. So this goes behind, fits like that, and then the sprocket goes on as normal with the snap ring on top of that, and that basically locks the sprocket onto the output of the hub, so I can get the two power readings to say the same. I have power data being received on this one here as the red light's off, so it's connected, and you should be able to see it's transmitting every time it receives power data from the pedals. It also reads the power from the generator and then transmits it out, which I shall show you next. To prove the data on here is actually from the pedals, I've got my cycle computer connected up to the Garmin pedals. So the top graph will be the power from the pedals. This one is power from the generator being calculated with an equation. Now these two won't match up at the moment because I haven't fiddled with the values to make them equal, and that's the next stage. And at the bottom here is the resistance setting, Now I've got this to change automatically so that when the power here is above a set value, the resistance will increase, and when it's below, it will decrease. So I shall just demonstrate this. It will calculate the efficiency as it goes along, and it's going to display it on this lower graph here. That doesn't mean anything at the moment, the hub is locked. So I think I've summarized the basic principle of how the setup works, so I'm now going to go into the boring details, or at least some of them, for anyone who is interested. This is some data that I've literally just recorded, and here's the efficiency that has been calculated. And as you could probably tell earlier from the data, the previous clips, it's reading a little bit low for the generator power, which is the blue here, and then we've also got cadence, open circuit voltage, and current down here. Now what I've got to do next is to change these values, which is in this equation here, to get it to 100% across the entire test. And those values will be put onto the Arduino, and then it should read 100% while the hub is locked. This equation accounts for all sorts of losses, basically every kind of loss, so that could be air resistance on the wheel, to chain friction, and so on. And also what I discovered was that because this is slowly ramping up and down, there is a flywheel effect as well, which I've had to account for here, which made it even more challenging. But I'm getting reasonably consistent 100% if I change the values, which I shall have a go at. I changed a few values and got as far as this, which isn't too bad, but also it isn't that great either. It's certainly not really going to have any potential for giving accurate figures for the efficiency, but it can certainly give a rough idea of the overall picture of what the efficiency is like at different hub ratios, for example, and at different power levels. To still see here, it's a little bit of that kind of flywheel effect, maybe, at very high RPM, very low current. That's about as far as I've been able to take it for the moment. Perhaps I'll be able to work at some better equations, maybe, but I think this setup perhaps has its limitations for all sorts of reasons. If I was to leave the setup and come back tomorrow, I'd find that these values sort of to change them. The efficiency would just be different again, only by a few percent, but it's something. And I think there's possibly all sorts of factors like temperature, chain lubrication, calibration of the power meter, etc. And so it really demonstrates just how many factors are involved when it comes to the efficiency of something. You might have been wondering how I got a smooth change in resistance from 6 different resistance values, these 6 here, and well, I actually ended up going back to PWM. This time though, instead of controlling a resistor entirely with PWM, well, I do at the lower end of these resistance. But what I actually do is share the current between a resistor and then a PWM controlled resistor alongside it, and that provides basically a transition between these steps. So these are the maximum PWM values. Took a little while to get those right, to get the smooth transition, but this seems to work pretty well. You can see various different combinations here to get the steps, and then the final one I just literally switch on one resistor after another to get the full resistance at the end. What I found with the Arduino Every is that actually there's one pin that it's supposed to have PWM but doesn't. This was the current that I recorded, while keeping a steady RPM on the generator as it ramped through the resistance settings. It turned out pretty well after a little bit of fiddling with some of the PWM values. And finally, I'll go very briefly through the Arduino code for anyone who's interested. And this is for the Arduino Nano Every, and I chose that one because of the ADC. It has the ability to put into free running mode, so it has a certain amount of averaging, which I thought was useful and makes it more accurate as well. But it did cause a few issues with the PWM. As you can see here, I had to learn about all the different timers used for PWM, and in the process learned that actually pin 11 does not have PWM, despite the board layout suggesting that it does. So that's the defines for pins and all the other parameters. Now the other thing to note with the Every is that the serial communication to the USB is different. It's serial. Serial 1 is to the TX and RX pins, which is actually quite useful but annoying if you don't realize that's the case. And then I've also got another serial communication here, which is the one to the NRF52. This is the setup of the ADC, and the timer setup for the 1 kHz interrupt to monitor the read switch. This is the ADC processing the value, the interrupt for the RPM, and in the main loop this is the serial data coming from the power meter pedals via the other board, and I've got that set up so that it sends a P before the power data and C before the cadence data. And when it receives these at a different rate due to the type of parameter that it is. It doesn't send them both at the same time, but when it sends cadence, that's when I do all the calculations here. So these are the equations for things like current, open circuit voltage, which I've added some smoothing to, and the equations, there's the flywheel effect, trying to compensate for that, the generator power, and then the efficiency. And I'm just printing this all to the serial port, and to both in this case, so you can get it on USB as well. And then these are for changing various settings. And the resistance control is the next part, which is here. This turned out to be quite complicated, because changing the resistance it means that you effectively make it easier or harder to pedal, which then causes the power to increase or decrease, and it can very easily lead to oscillations, so I've had to compensate for that as well. So the rate at which these change, the resistance setting changes, is different depending on which part of the resistance range it's in. Basically, it's compensating for the difference in the gradient of this line. So as you can see, it is quite different. So that's what these different values are here. They all got quite complicated, but it all works fairly smoothly now. So it's just all copies of just for each different resistor setup. So that's it for the Arduino code, and thank you for watching.